for all the efforts and for giving me this opportunity. I'm going to show some fresh stuff about PMN, fresh and unexpected, and these data are brand new. They are collected not later than in the beginning of December, basically. We'll give some brief introduction, well, rather introductory inserts through the talk. We'll show inconclusive and incoherent results of coherent scattering of X-rays. Well, that failed essentially, and then we collected plenty of suspicious diffuse scattering and made some conclusions which are questionable or fragile. We like to find it. Well, at one moment I decided not to touch PMN and relaxers anymore for obvious reasons. Well, too many people are working on this domain and too many different publications. And, well, basically, if you want to get to know what really happens, you have to remeasure. Sad but true. And the example, phase diagrams. We can find old good phase diagrams, which were overtaken later by more advanced, more detailed phase diagrams, which contains two really bad mistakes. I put round circles around. If you are aware about phase diagrams which are more fresh and less wrong, please let me know. So, well, in this case, you see the gap around x equals 0, symbolizing that PMN doesn't transform when you cool it down in the absence of field. And that's exactly what we observed, measuring this RF X-ray scattering. The diffuse scattering intensity on cooling starts to grow up below 300 something, and then it's monotonous and boring. But if you apply the external field, you can see the effects that, well, diffuse scattering becomes asymmetric under the application and symmetry is lowered. And then there is strange stuff happening with the surface layer ranging from 10 to maybe 50 microns with a structural distortion seen there below TC, around 200K. And, well, so I was a bit demotivated to remeasure PMN, but our colleague Yuri Chushkin still wanted to measure XPCS, X-ray photon correlation spectroscopy. Basically, well, I cannot and I have no time to go deeply to the details, but essentially with the coherent X-ray beam, we collect a lot of 2D frames containing speckle patterns, and then we merge them to 2D correlation function, which says something about the dynamics, about relaxation times, about aging, absence of aging, or, well, it's quite developed domain and not that transparent. Tricky thing that to have good coherent fraction in X-rays, you have to go to rather low energy, and the sample has to be thin. And the ideal sample would be something like 10 microns needles, which is not obvious to cut. Well, I cannot cut, so I had to cut, polish, and then etch down, removing about 20 microns of surface. That means that essentially we can exclude that there is some built-in strain due to cutting and polishing. This surface just gone. And, well, there are nice graphs, nice data, rather reproducible. The interpretation can be that, okay, for 260, just believe me, this is the relaxation behavior. So we have some decay, some destruction of correlations between the speckles in frame 1 and frame n. And it doesn't evolve too much during the real time. If we cool down slightly further, you see that it changes a lot with the real time. That's the aging effect. And this is kind of classic behavior for aging system. Then we go further down, it becomes strange. So something happened, then system changes its mind, and it's not that easy to explain. And below, when everything is frozen, well, nothing happens. But if we don't don't look to the correlations, but we look to the integrated intensities, there is sudden drop of intensity below 200K or something around that. And this is kind of unexpected because we have seen, but we have seen on fake sample, on 100 micron sample, that nothing happens. Diffuse scattering just grows up. So that was the moment to measure diffuse scattering again and again. Now it's easier for me because I have my own diffractometer, well adapted for measuring diffuse scattering with good beam, good focusing, very good detector, and well, not much waiting time to get the beam time. And here I put the stacks of individual images taken in the proximity of one drag, 110, as a function of temperature. So we heat up, there is sudden change. We cool down, there is sudden change at different temperature. We heat up again. It's perfectly reproducible comparing to the first column, first pile. So something happens, phase transition. There is hysteresis. That happens exactly at the temperature where you would expect transition to rhombohedral phase, which supposedly doesn't happen in pure PMN. If we change the scanning time, transition temperature moves, so there is some kinetics behind, but it doesn't change the conclusion that something happens, something drastic. And we collected full data sets for a number of temperatures, and here I put the example at 150K, 120K. I use always a notation for pseudocubic lattice, okay? And here you can see that HK0 plane doesn't satisfy four-fold symmetry anymore. Some HHL planes contain mirror planes, and some of them do not. And here the difference is quite substantial for R point intensities. Here you see the contrast. And these two spots are equivalent in cubic phase. So system becomes rhombohedral, and it's quite pure single domain state. Otherwise, you would have more equilibrated intensities. And well, there are some trends that diffuse lines are less or more aligned along a threefold axis. But not exactly, because they are along 110 and threefold axis is 111, 35 degrees off. And another family is just dying. If you look to 3D reconstructions, it's even better visible. So here is the threefold axis, which is now dead. There are 3 of them, which are destroyed, and 1 survived, and it looks quite different. Yeah? And this is former butterfly. Here, it was 4-fold axis. Well, at best, you have 2-fold axis now. And here, you can follow the evolution in the proximity of 100 spot. So a symmetric butterfly becomes quite symmetric around the transition, around 200. Then we have peak of diffuse scattering intensity, which behaves like Q minus 4 at around 250, and then it decays, and it re-becomes Q minus 2, and weakens on healing. That's about what we have seen before above TC. What is behind? I have no decent explanation. Single domain R structure is not due to the sample shape, because all the domains would have the same angle with the needle axis. So this is not the reason to have preferred orientation. Maybe frozen in asymmetry of niobium-magnesium correlation pattern, something which we don't see. It's somewhere hidden in the diffuse scattering, and it's quite difficult to track back. Could that be that it's skin-only sample? Yeah, if skin is 10 microns and we have 10 to 20 microns remaining, we have no bulk in this sample. Or maybe just for this small and that good sample, we have unusually large hysteresis. So we go to 80K and we are still not in low temperature phase usually. But here, hysteresis is narrow and we get something. It was not the last surprise. Another surprise is observed in supposedly cubic phase, around 250. So left panels, rhombohedral phase, this is supposed to be cubic above the transition. And what in cubic, butterfly looks symmetric. Unless you look with different oversaturation level. They are asymmetric. And this asymmetry, again, fits with rhombohedral symmetry. If we would not have single domain rhombohedral structure, we would have no chance, absolutely no chance to observe this asymmetry. So having detwinned sample is essential. And yeah, it was a question of luck. Well, now we know that we can link this asymmetric diffuse scattering to the domain structure, and we can simulate the effects of electric field application in the same way. So I took old data for PZN, and I took new data and simulated the pictures for exactly the same HKL sets. And you see that the agreement is quite remarkable, qualitative and nearly quantitative, despite of the fact that the system is different. Temperature is different, and well. So, all the effects of electric field in this case can essentially attribute to the domain redistribution under the field. Another example, well, you can trace it back to this workshop 2 years ago, where quite live discussion was exposed, and then it was a follow-up published. I mean, this neutron scattering data. PMN PT sample, which should be rhombohedral in this state, was measured with neutrons, was poled sample, and some features were identified as PNR related. What surprises me here that these branches, which are supposed to be PNR related, they look as nice as the branches from normal bulk. Then I was a bit surprised to see that 100 polling was applied, which essentially suppressed 4 domains over 8. And everything you obtain in HK0 plane, except for 100 and 110 directions, has twice more phonons than you would like to have. So even if you don't touch the multiple scattering effects which are present, this interpretation is at least questionable. Well, a bit of lyrics. There is a Russian expression saying pulling the all over the globe. It means, for instance, making strong conclusions from weak or non-existing evidences. And I would like to ask for a favor. When you want to say something about polar nanoregions, stop for a second and think about this poor bird. Well, another surprise from PMN, from the same sample, already the third one. Strong spots appear at the endpoint on cooling. And if we trace the intensity as a function of temperature, the increase is quite drastic. Or you can represent it like this. So it starts to grow below TC, And it keeps growing until at least 80K, and I can even suspect that it can transform to another phase on further cooling. For the moment, I had no possibility to check it, but I will do that for sure. So to sum up the observations, PMN can transform to R phase without field, whether it's sample dependent or sample preparation dependent or something else dependent, it remains to discover. First thing I want to check next months is to measure diffuse scattering as a function of temperature for the samples from the same batch of different thickness. If it's skin effect or not. Cubic PMN can be less cubic than expected. And something else can appear at low temperature. And this low temperature phase probably will be less sample dependent. There are questions concerning the phase diagram. Still, maybe new fields will appear and maybe old fields can be slightly redistributed, slightly retraced. And well, I still have seen no indications of PNRs in diffuse scattering. I don't know whether they exist or not, but I don't see them in diffuse scattering. Okay? And well, if still you have choice, don't touch PNR. Thank you.
Yeah, we have several minutes for the question. Circa, please.
Thank you for nice new results, challenging ones. I think what could be the issue now to discuss is what is the origin of the skin in PMN-PT, because in the old times in ferroelectrics, there was discussions whether skin layer is intrinsic, just the effect of the surface, or due to the fact that we do something wrong to the surface, like polish the crystal, etc. So if it's the intrinsic phenomenon, then it may be that your sample, which is, please remind me the thickness, but could be all surface-like. So if it's like natural property of PMN to be polar, it could be the explanation of your measurement.
Yeah, definitely. That's what I suspect. Then the question is, what is more natural, the properties of skin or the properties of so-called bulk? Ask me again in a couple of months. I will compare thick and thin sample and probably will be able to answer.
So some years ago, we did DFT calculations and found rhombohedral phase and a monoclinic ground state depending on chemical ordering. So do you see any evidence for chemical ordering?
Well, I always see the chemical ordering in air point, sodium chloride style, magnesium niobium ordering, and actually this diffuse scattering data in rhombohedral phase are good for checking some models because there is interference term with lead displacement. Some of them becomes weaker and some of them stronger when lead is aligned along single threefold direction.